Okay, so right now we're gonna go into the Solow Growth Model. So this is actually just named after a random guy named Solow. And this is exogenous growth. It's like about exogenous growth. Exogenous is like external. I don't really know why it's external growth. So it's like everything is made up of like capital and labor, which is like internal, I would say. But I guess maybe I don't really know what they're talking about. So let's start off. So some like important starting information. So like some basics, I guess, is so let's start on the consumer side. So first of all, N is population. Remember, anything with an apostrophe means future period. So the future population is 1 plus N times the old population. In this case, N is the growth rate of the population. So it's like, like with like investments, always like 1 plus R and then times like old, it's like future value equals 1 plus R times whatever, like dollars, something like that. I don't know. Anyway, basically that's basically it. And one condition is that N is greater than -1. So why is that? Well, we'll see. If N was like -2, for example, it would mean that N thing equals 1 minus like 2 times N, which would mean that's like -N, which means that the population is negative. So to make sure that that never happens, we can't have it less than or equal to 1. So it has to be bigger than 1. Because if it was equal to 1, the whole population would be 0, which doesn't really make sense. So it has to be greater than -1. Now if it is, so now it could be from like 0, -1, and anyway here. If it's in this range over here, that means that the population is decreasing. So like N1 equals 1 minus 0.5, I guess, times N, which means like 0.5N, which is like half the old population. And anything above 0, so in this area, would just be like normal, like populations, it's like growing, yay. So it's like, let's say 1 plus 0.5, so it's like 1.5, blah blah blah, whatever. Anyway, so this is just like a condition you need. Another thing in this like model is that leisure is not considered to be like a thing here, I guess. Like, I don't know, I guess I don't have any value for leisure. So basically people only work, they don't take any time for leisure. I guess that's just to make it that's either to make it simpler for us right now, or it's because the model is actually set up that way. I'm not really sure. Anyway, so that's that. And another thing is there's this formula, there's like this quick formula. Consumption equals 1 minus little s times y. Little s is the savings rate. So savings rate would basically mean like for example, what the hell is that? Like the total amount of savings that we do is equal to the savings rate times our total income. Like basically, like let's say that I save 10% of my income. So it'd be like 0.1 times the y equals how much I save. So that rate over here is the s, little s. So basically like that. So you can basically write this like our normal way. So I wrote like a little thing to write the proof. The proof is, it's kind of, now that I look at it now, it's kind of dumb, but like, let's just go over it. So with the money that we get, we either consume or we save. Rearrange that, we get y minus s. So C equals y minus s. Okay, and then the amount that we save is our savings rate times the total income. So y 1 minus s, and that is also this formula right here. C equals 1 minus s times y. Great. Blah blah blah. That's one thing. Okay, so the video accidentally paused. I'm not really sure where we ended off, but as far as I remember, it was at the point where I basically showed that this thing over here, the proof, blah blah, we get that C equals 1 minus s times y, 1 minus s times y. Great. Next, the next we have is, right, so now that we've gotten through the consumer stuff, let's look at it from the firm perspective. So first of all, we have our normal, like our normal equation. Output is the factor productivity times like a function, like some random function that is made up of both capital and labor. Cool. Next is the CRS, so the constant, the what? Fortunately, what are you doing? There's constant returns to scale. Oh yes, that's what it stands for. Constant returns to scale, which means that this thing over here. If I were to increase the capital and the labor by some amount lambda, is this lambda? I think so. I think so. Whatever. If I increase like my factors by this amount, then my output will also increase by the same amount. Cool. Now we're just gonna let this lambda be 1 over n, so like 1 over the population, or like 1 over the workers. Oh, you know what? I kind of get why the leisure is bad thing here, because usually, you know, we'd have like normal people and then workers too. You know, like you can be like a normal person and like not work. But in this in this thingy over here, where the hell? Oh, gone a bit too far. In this thing over here, basically the entire population is working, and like, so this is like the entire population. So like when you divide it by the population, it's like the entire population. So you can actually say like per capita. Whatever, anyway. So let's just replace all the lambdas in this formula with 1 over n. So if we do that, we get this, n over n, blah blah. So it comes to y over n equals z fk, k over n, comma 1, because n over n is just 1. Which is kind of dumb, because like, why would if it's going to be 1 forever, like just take it out. Which is what we're going to do. So next, let y equals, oh, okay, right. So now we're just going to we're going to give like letters to each of these. We're going to, oh, I don't know. We're going to give letters to each of these little like big variables, because, you know, we want to make it smaller. So like this little y is going to be big Y over n, which is like output per worker, and little k. So I know it looks kind of like an R, but it's supposed to be like, you know, like the fancy k, like this, whatever. Anyway, so little k is big K over n. So that is the capital per worker. So like how many machines each person has, whatever. And one thing to remember is letter D, which we'll be using later on, is a depreciation rate, and the D is like between 0 and 1. Cool, cool, cool. So now basically we can rewrite this function over here with these letters over here, and we get little y equals z times function is a function of the little k, because remember, we're going to kick out that 1 because the 1 is sort of useless. Great, next. We're just going to plot this, like, basically, so we have a... So we're gonna plot, oh, right, okay, this is, so we're gonna plot this, and we're gonna plot it as capital per worker versus output per worker. So like, basically it's like, oh, okay, this makes sense. Okay, first of all, this has like a slowly diminishing slope, which I'll go over. So first of all, if each person has like, let's say that, Varshney, I'm making a video right now. Let's say that I have to wait like a really long time. Hold on. Okay, let's say the capital per worker is like is 0.5. That means that each person has 0.5 a machine, which means that let's say like I'm sharing my machine with somebody else, you know? There's like one machine and I have to share, and it's like, oh, I have to wait for this guy to go. That kind of sucks, right? So if this thing were to increase, if this machine per person increases to like 1, then we each get our own machine, and that's sort of like, you know, like for a while it sort of like you know, it like makes it better, because it makes it better and we each produce more, so like the output that each person produces goes up. So, you know, initially sort of like goes up, it's an upward slope. But thing is, as you increase them more and more and more, let's say we get to like 3 machines or like 4 machines, you know, let's say I have like 4 machines now. At this point, it's like there's so many machines that it's like I can't even keep control of them, you know? So like adding 1 more machine, I'm gonna be like, bro, like what are you doing? Like I can't I can't control all these machines. So as you increase them more and more, as the capital per worker goes up more and more and more, like the output per worker doesn't increase as much, which is why the slope is like up, and then it slowly like becomes flat. Cool. And the slope is a marginal product of capital. So because it's basically like, It's output per worker divided by capital per worker. We can just cross out the workers. It's just output per capital. So how much output does each additional, like, how much output does each machine make? Which is like the marginal product of capital. Cool, cool, cool. Whatever. I mean, this is like a way oversimplification, you know, like this is like not how slopes work, blah, 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 whatever. It's not really important. Cool, cool, cool. So I get this. So it's just like a little, I don't know. This, I think it's just like a graph, just so you can like look at it visually, whatever. And it's just like y equals this fk zfk formula. Cool, great. Next, let's go to the next section. Competitive equilibrium. Oh boy, this is gonna be longer than I thought. So we have capital, future capital equals 1 minus d plus the old capital plus I. We went over this in the last thing. Basically, it's just the new capital is like the old capital times like however much depreciation has gone through, plus like any like extra investment that we made to like make the machine bigger or better. And that is how much capital we have now. Great. So now I'm just gonna rearrange this to put I on one side and then move this guy over here. So we get this. Okay, great. Now we know that S equals I, so I think this is like just like how savings equals investment in a closed economy. Like I remember making like a video about that. I don't know if that's the same thing as this or if this is like completely different. Nevertheless, it's savings equals investment. I mean, like, you know, like with the money, like with the extra money that you, okay, I guess, okay, one way to think about it is with the extra money that you get, you're either going to save it or you're going to invest it. I don't know who you are, like if you're like a business owner, pretend you're a business owner, I guess. With the extra money, you either save the money or you invest it. So it's going to be like equivalent, like you have the option to do both. So it's like they're both like an equal sort of amount. Like you have like the same amount of dollars to each thing. Okay, whatever. So you have this thing over here. And now let's look at this formula here. Y equals C plus S. Replace the S with the I, so C plus I. Now C equals 1 minus SY. We know this from that formula, you know, like the very first thing that we did with like the S times Y and like all that stuff. So that's that. And then the investment is just this thing over here. We plug that in, great. Now we rearrange this whole thing to put K future on one side and then everything else on the other side. We rearrange, blah, blah, blah. So we get this over here. We get this over here. Y is like the ZFKN stuff. So we replace that in. Now we're going to divide everything by N just to get like some per worker values, because for some reason using per worker values is really great. So we're going to divide everything by N. Cool, cool, cool. And now, oh, okay. So just forget about this thing for now. Oh, I shouldn't have done that. Okay, whatever. Forget about that part for now. So just dividing everything by N. So basically this, when you divide this part by N, it's like you're dividing this function by N, right? Kind of thing. So it's like K over N is that little k, and then N over N is 1. So it's sort of like back to that little equation where this whole thing turns into just this f little k. So that's how it converts. 1 plus dk over n, this is little k. So it just converts over there. Now for this k over n over here, well, we're like, bro, like, there's no way to do this. Kind of like, you know, like this is like future period, this is old period, what are you supposed to do? So we're like, okay, let's just multiply both sides by n apostrophe, n apostrophe. And now we're going to look at, ooh, different colors. We're going to look at this thing over here. So that is, oh, this might be too dark, whatever. Okay, why? Oh, okay. So this is like big K, big future K over big future N gives you little K. That gives you this, okay? And then this over here, oh, look at all the cool colors. This over here, this future N over past N is just the growth rate, 1 plus N. That's so cool, you know? So now that we have this, we are gonna go back to, alright, so now we end up with this. So, oh my god, this color is so disgusting. Okay, so now we get to this, and then now let's just move this 1 over n guy to like here. So we're gonna do that. And so our final like cool formula that everybody likes is this guy over here. So this one over here. So basically, I'm not gonna read out the formula, but this is the capital per worker in the future period. And this over here, this is the capital per worker in like the current period. So basically, this is sort of like the future capital as a function of like the current capital, which is pretty cool. Like, you know, like using, like given the current one, the current K, I can find the future K. Find these. So now, like, there's like two like little like chunks. The first chunk, I think it's basically just like the production part, because it's, you know, it's got like the Z and like the F and everything, so it's sort of like the production part. And this thing over here, I mean, like, considering there's like the 1 minus D and like the little k, like capital stuff, I guess it's something like related to like the machine left over. This is not accurate at all. I have no idea what this is. Because the thing is, you can't really break it up nicely, because in the very first part, like over here, like we rearranged everything, right? And we rearranged everything and we like moved stuff here and there. So there's no way to like clearly like label each of these two chunks. But I guess that's just like one little thing you can do. Whatever. Anyway, the last thing, one of the last things that we're gonna do is steady state. So basically, in this formula, you can see that, you know, as the k increases, this future k also increases, which means that there's like a positive relationship between the first k and the future k. And this curvy line over here is that relationship, the whole formula thing, whatever. So now what we're gonna do is we're gonna be like, oh, look, given a current like k0, like k, like right now, we can go up to this curvy line, and we'll be like, oh, look, when you go to the left, this is a future one. Damn it, k1. So that is pretty neat. And like, you know, we just go back here. Oh, okay, this is a bit confusing. And then after that, we just go, like, at any point, when you go from here and you go up to like the big line over there, and you go to the left, that's like the 1 plus 1, like the next one. Wait, why does that say 3? It's supposed to say 2, so this is supposed to be this one. Like basically, if I have like k1 here and I go to the line, the one that's on the left side now is k2, because it's like the future one. Whatever. Anyway, that's that. That's fun. And basically, like, okay, so if you see over here, you can actually sort of see it visually too. You can see it visually too. This, okay. Over here, like right over here, like k0 is really small, but k1 is really big, which means that it's like from the first period to the next, it grew so much, you know. Then over here, k1 compared to k2, it's also like growing like a lot, whatever, like not growing a lot. Like this k2 is bigger than k1, you know. But the thing is, as you go higher and higher, like they're like almost the same distance. Like this k2 is like almost the same as k3. Basically, they're saying that we'll get to a point, this k star, the steady state, which is a point at which the k before the k like current is equal to the future, because like it's a point at which like the 45-degree angle like intersects the curvy line, so it's like equal. So that's like a cool thing. Steady state, it's apparently pretty important. So I guess where the capital at period 1 equals period 2. Great. Yeah. I think that's it for this. Okay. And we're gonna end off with just like some intuitive stuff, I guess. I hope. So per capita variables. So, all right, okay. So now we're gonna look at like some growth rates of things. So first of all, we're gonna let this symbol over here. I don't know what this is actually. Whatever. Well, let's just call it a U for now. Hold on. This is whatever. I'm just gonna have the growth rate. So the growth rate of X is just gonna be used like this symbol. Great. So for per capita variable, so first of all, for like the K, for like the baby K, so baby K star, so baby K star never changes. Like it's literally just baby K star kind of just depends on this function here. So basically, as long as the function doesn't change, the baby's K star isn't going to change. And like the function is not going to change. Okay? So the baby K star is not going to change, so it's constant. So the growth rate of the baby K is 0. Next, baby Y, well, baby Y is basically like Z times a function as a function of baby K, and since baby K is constant, baby Y is also constant, so the growth rate of that is 0. Now, again, baby Y is constant, so over here, for the baby consumption, wait, this is baby? I think this is baby consumption? Okay, I'll make like a note at the bottom of the video, I guess. I'm pretty sure this is baby consumption. Yeah, okay, this is baby consumption. Like per capita consumption. So baby consumption depends sort of like on, like the baby Y. And since S is just like a rate, like our savings rate, which isn't going to change, like, this is given. So baby C consumption is also constant. So the change in growth rate of baby C, of baby consumption, is 0. So all these per capita variables are basically like constant. Their growth rates are 0. Now we're looking at total variables. Now for total variables, all of these growth rates are n. So if you look here, it's all n. And now this is because because of this guy over here. So this is like the main guy. So basically, our total capital is a capital per worker times the number of workers, right? Right. Now we're looking for the growth rate of the total capital. So basically the growth rate of this, which is equal to the growth rate of this, since this thing is constant from like, it's like baby K is constant, it has to be the growth rate of this. And is n constant? No, it's not. N is population. Population is always growing, and what's the growth rate of the population? Baby n. So basically the growth rate of big K is baby n. So the change in this is baby n. Now we're going to use like the same sort of thinking for like the rest of things. So big Y equals baby Y, baby Y times n, like times the population. So the growth rate of big Y equals little n. Same thing for I. So I equals S times Y, for example. Oh, right, okay. Right, this is because I equals S, right? Savings equals investment. And S equals baby S times Y. So we can just write it like this. And we can replace oh my god, I erased it. We can replace this Y with the function formula. And again, this is ZFKN. So the thing is, it's basically like ZFK times N. We can sort of also put like this N back in the function and make it like this. But like, like basically like another way to do it is also like this little baby K inside and then multiply it by N. Because we're sort of looking at like baby variables. Could that always, right, because we're looking at per capita variables. So like it kind of could work, I think. Anyway, whatever. So like this is like, one way to write it. So again, we have, these guys are all constant. Baby K is constant, so it's the same thing. Change in N, which is N, blah, blah. C equals Y minus S, 1 minus SY. Again, we pull in the whole production function, so it is also N. And that is it for today.